So this is a quick walkthrough for the sample assessment materials for the new SIA specification of GCSE Physics, and we're looking at Unit 1 higher tier. Okay, question 3A, part 1. You're provided with some coins, an electronic balance and a graduated cylinder which already contains 30 centimeters cubed of water as shown below. Describe in detail how you could use the apparatus to find the density of the metal from which the coins are made. You already know the mass of the coins and the volume of the water in the cylinder. So the density row is mass over volume. Now we already have here a mass value. What we need is the volume of these coins that we're interested in. So we need to take these coins and use them by putting them into the measuring cylinder there and measuring the increase in volume registered when the coins are put in. So you need to give a description basically of adding the coins carefully, taking a new reading of volume, finding the difference between the current reading and the new reading, and that will be the added volume of the coins. Once you have a mass and a volume, you can go back to the density equation and calculate mass divided by volume. So when you add the coins, the level will rise to a new level somewhere here. We don't know where that will be, but when we add the coins, we will get a new reading, and the difference in these two readings will be the volume of the coins. Once you have a mass and a volume, you fill them into your equation, and that's what you want to explain in the lines below. I'm not going to spell it out for you just for speed's sake here. Next, they ask you to perform a calculation by telling you that the combined volume of all the coins is 12 centimeters cubed and their mass is 107 grams. Calculate the density of the metal from which the coins are made. So you start with your row density is mass over volume, and then you substitute numbers into that, 107 divided by 12 centimeters cubed, and that gives you 8.9 grams per centimeter cubed. Part B, use kinetic theory to describe the way the particles are arranged in a liquid. So the particles in a liquid are pretty close, but there's no sort of regular arrangement. Remember, the particles have a bit more energy there, and therefore they can move past each other, so they don't have a specific arrangement that they have fallen into. Part 2, explain in terms of particles why liquids have a fixed volume but take on the shape of their container. So for fixed volume, we talk about them not being compressible because they're already pretty close. And for taking on the shape of the container, we explain that they have enough energy to move past each other, and that allows them to fall into any shape. Explain why the density of liquids is generally greater than the density of gases, and that's obviously the fact that gas particles are much further apart than liquid particles, and so gases take up much more space and have low densities. So because the gas particles are farther apart, they take up a bigger volume, which gives them a lower density. Question 4a, a metal is a good conductor of heat, glass is a poor conductor of heat. Describe in terms of particles how the conduction of heat takes place in a metal and in glass. And so obviously in metals you've got vibration between metal atom to metal atom, and then you've also got the significant contribution of the free electrons racing around inside the metal, a bit like gas atoms. They can move very far down the metal very quickly and strike ions much further down the metal, whereas the normal particle-to-particle vibration requires a contact with neighbours and so takes much longer. Glass only has that particle-to-particle vibration, and so it's, you know, your standard vibrating at the hot end. That vibration passes on to neighbours, that passes further down, and so you get very low levels of conduction in something like glass. And the mark scheme seems to just talk about the free electrons in the metal, not mentioning that they would also have available to them atom-to-atom vibration. But there you go. Part B, describe how you would use the apparatus shown below to investigate the difference between the emission of heat from dull black surface and shiny white surface on the two cans below. So we assume these two cans have these surfaces painted onto them, dull black, shiny white, and they've got hot water in each, they've got a thermometer in each for us to monitor them, and it then sort of specifies what you're supposed to do. It says in your answer you should state the features of each can which ensure that they represent a fair comparison, and that's the kind of thing like they must be identical cans in every way except for the colour of their surface. So they should be made of the same material, the same size, same thickness of wall, etc. All the properties of the metal that the cans are made from. State what quantity should be the same at the start of the experiment. Okay, so you're going to be looking at the volume of liquid in these two containers, and the temperature it goes in at would need to be the same. What measurements should be taken? Well, what you would do with an experiment like this is take temperature, say, every minute for a half an hour or so, and look at how the two temperatures are changing in some kind of graph. So it says state what graphs you would plot. You're going to plot temperature versus time for each one of the temperatures. You know, we call these A and B. This is where you could sort of help yourself a little bit by deciding which one's which. So using the same set of axes, sketch the graph that would be obtained for each can. You should label one graph dull black surface and the other one shiny white surface, so they expect you to know the outcome as well. State what measurement is used to decide the better emitter of the heat. Okay, so you want to know what that graph would look like. Let's go over to the graph. So here we are at our graph, and we're going to want to have like temperature running up this way, and we're going to have time running this way. So axes, something like this. We've got nearly half an hour's worth of results here. If we go in minutes in twos, we get all the way up to like 24, 26. And if we go 10 per one of these squares, we get all the way up to 100. And so we would plot that, and we would find a couple of things. One, there's going to be behavior where these things will head towards room temperature. So just bear that in mind. They're not going to get colder than room temperature because heat flows naturally from a warm object to a cold object, and so when they reach room temperature there is no warm object or cold object. Both the surroundings and the cans will be the same. So if we have this, say starting at 80, one will come down fairly quickly, one will come down slower, still heading for that same point, and so the dull black one will be the one that cools quicker, and the shiny white one will be the one that cools more slowly. So you'll end up with something like that. Part C, a swimmer in a 100-metre race exerts an average force of 80 newtons to move through the water. Calculate the work done by the swimmer. Okay, so they have a force here of 80 newtons, and they're covering a distance of 100 meters. So work is force times distance. This is straight out of your notes, just filling in an equation. So work is force times distance, 80 newtons times 100, and that's going to give us 8,000 joules. Part 2 then, the swim lasts for 40 seconds. Use your answer to part 1 to calculate the power of the swimmer. Include a unit for the power in your answer. So this is power as work over time, again straight out of your notes. Okay, so we take our 8,000 joules and divide by our 40 seconds. And that gives us 200 joules per second, which we call watts. Part D, the graph below shows how the gravitational potential energy of a stone changes as it falls. On the grid, draw a graph to show the total energy of the stone during the 4 seconds of its fall. So in a situation like this, we would assume that there's no energy loss, so that the 400 joules of GPE it starts with remains the total energy during the entire motion. So you've just got a straight line going across the top there. We just go across here, and that would look like that. So the total energy remains constant if we assume there are no losses as it falls, and that becomes relevant later. Part 2, calculate the height from which the stone was dropped. The stone has a mass of 0.25 of a kilogram. Well, we know that the GPE at the beginning was 400 joules, and we have an equation for GPE. The gravitational potential energy is m times g times h. And we can just look at some of those terms briefly. So as said before, the GPE is 400 joules, the mass 0.25 of a kilogram, h is an unknown, and g is 10 newtons per kilogram for gravity on the Earth. So rearranging for h, we get that h will be the gravitational potential energy over mg. And that's going to be like 400 over 0.25 times 10. And that gives us an h of 160 meters. Part 3, state the kinetic energy of the stone after 2 seconds. Now we need to go and look at our graph to sort this out. So the GPE is falling, and by 2 seconds here it has fallen to 300 joules. Now remember, when the GPE decreases, the kinetic is increasing. So the total energy is still going to be 400. So by the time the GPE has fallen to 300, the kinetic will be this 100 here. This value is going to be 400 minus the current value of GPE, which is 300. So 400 minus 300 gives us 100 joules of kinetic. Now they ask us to calculate the velocity of the stone after 2 seconds. So we're obviously meant to make use of that 100. So we've got 100 joules of kinetic energy, and we know the mass of this object, so we need to look at our kinetic energy equation, that kinetic is a half mv squared. So rearranging that, then v would be, we would need to double both sides to get rid of the half. So 2 times the kinetic energy would mv squared. 2 times the kinetic energy over m would equal v squared. So v will be the root of 2 times the kinetic energy over m. And so that's going to be the root of 2 times 100 over the mass, which is 0.25. And that's going to simplify to the root of 800, which works out to be like 28.3 meters per second. Question 5a. A beta-emitting radioactive source is placed in front of a detector as shown in the diagram below. The radioactive source is surrounded by a substance X on all sides except for a narrow opening on the right. What is a beta particle? Well, beta particle is just an electron. That's straight out of your notes again. For substance X, you would need a material that would block a beta particle, so you're best going for something like lead. Give 2 reasons why the substance X is used in this way, and if you think about that diagram, you're wanting to shield the user and only have the particles come out in a direction which we're aware of, because obviously they're invisible. So you want the user to know, a bit like if they're holding a torch, which way the radiation is coming out of it. So you're trying to protect the user, which is basically the idea of shielding. And you're going to give the radiation a specific direction. In this case, it's going to come out of the opening. Describe what happens to the number of beta particles detected as the radioactive source is moved away from the detector. So if you keep increasing the distance, some of the betas will be absorbed by the air in the atmosphere, and some of them will spread out and miss the detector. That happens with any source. It will spread out a little bit, and so it will definitely decrease if you do that. How far must the radioactive source be placed from the detector so that only the background radiation is detected? Well, for beta particles, that would be several meters. The radioactive source is now placed close to the detector. What two absorbers could be placed in the gap between the radioactive source and the detector so that no beta particles are detected? And the standard absorbers we would use would be things like lead and aluminium, so I would stick those in. Give one reason why even a weak radioactive source should be handled with tongs. Okay, so you don't want to get into too close proximity to them no matter what strength they are. So the idea of tongs keeps you from touching them in any way. Like for example, if a source had deteriorated and had become, the container had become coated with any kind of material from the containers that they're kept in, you could transmit that onto your skin and that would be a hazard to you. So it's just basic safety. Radiation is dangerous to human cells and therefore you should keep it well away from you. Okay, part B then. Yttrium-90 is a beta emitter which decays to zirconium. Complete the decay equation below for the beta decay of yttrium, which is Y, to zirconium Zr. So this involves just some basic arithmetic. We have to put in the properties of a beta particle. So we put 0 in the nucleon number column and -1 in the proton number column, because it's sort of the opposite of a proton, it's a negative particle. And then we just do the maths either side of the arrow here. We have to get 39 on the right in the lower number. So that would mean there would have to be a 40 here to go with the -1 and give us 39. We have to still get 90 in the top line, so 90 plus 0 would give us that, and you're basically just filling in your numbers to match either side of that arrow. Okay, a radioactive source contains 2 micrograms of yttrium-90, and apologies to the chemists if I'm not saying that correctly. Yttrium-90 has a half-life of 64 hours. What mass of yttrium-90 would remain after 192 hours? Okay, so how many half-lives is 192 hours? That's what we want to find out. And so we need to divide the 64 into it to find out how many half-lives that is. So 192 over 64, that's 3 half-lives. So we're starting off with our 2 micrograms, and then we have 1 half-life, and that gets us down to 1 microgram. Then we have another half-life, that gets us down to 0.5, and then we have another half-life, and that gets us down to 0.25. So 1 half-life, 2 half-lives, 3 half-lives, and the answer then will be 0.25 of a microgram left over. Halving it, remember what that is? It's basically times 0.5 times 0.5 times 0.5. Each half-life is the halving of the remaining undecayed yttrium-90. So halve it to 1 microgram, halve it again to half a microgram, halve it again to 0.25 of a microgram, and that's our final value. Part C, nuclear fission and nuclear fusion are 2 processes that release large amounts of energy. Which one of them is the source of energy in stars? Well, that's fusion. That's straight out of your notes. What important peaceful use is made of the other process? Okay, so that's obviously nuclear power stations. So generating electricity, nuclear power stations for that one. And in terms of what happens to the nuclei involved, explain the difference between nuclear fission and nuclear fusion. And so fission is the splitting of larger nuclei to release energy. And fusion is the joining of smaller nuclei to release energy. Or you could use terms like more massive and lighter, something like that. I like larger, smaller. And that is that.